problem that we are addressing when we're dealing with this type of situations is we've created a system, and that system has a tendency to be quite stationary. So we create rules and they enter the codes. The evolution of the code is very slow, and we educate people with certain competencies and skills and attributes, but those people have 30, 40-year careers. So the evolution of our training practices tends to be very slow. So we many times enter situations in which the evolution of technology moves much, much faster than our capacity to respond. And at that point, what you start creating is effectively dormant systems that are potentially not going to respond. Okay? So in reality, we end up with a situation where you have buildings where you know that the fire is going to happen, but we are not managing it appropriately. Now, the truth is that fires that are of any significance that actually make it to the newspapers are extremely rare events. And it is not because the probability of a fire is very low. It is because, despite the probability of one, we are doing our job correctly. Okay? So we've put enough into buildings in such a way that we are managing these events in a regular way. And it only happens occasionally in time that we create a situation by which technology overtakes us, and all of a sudden we realize that we are not managing the problem properly. And when those fires happen, then the consequences are unforeseeable. Okay? Now, unfortunately, many times this happens after we have built hundreds and hundreds of buildings with certain characteristics that effectively result in an inadequate protection of the building. Okay? And this was the case, for Grenfell Tower. So if you ask yourself the question, how could this happen? There could be no simpler building to design, that a very simple residential high-rise. In principle, that should be the simplest possible building that we could imagine. These buildings are so standardized in nature that we should have a very well-defined solution. And that very, very well-defined solution should actually perform appropriately. And there's absolutely no reason to believe that in such a simple building, we could potentially land in a situation like this. Okay? Needless to say, before this happened, there was enormous confidence among everybody that these buildings were perfectly safe. Okay? Today, 2 years later, we call them high-risk buildings. And you wonder why, no? All of a sudden, our perception has transformed itself. The day before Grenfell, all these buildings were deemed to be compliant. They were done under prescriptive rules. They were classified in a certain way, high-rise residential buildings. And as such, there was a solution, and that solution was deemed to be compliant. Okay? The day after Grenfell, the government started testing the buildings, and they found that 100% of them were non-compliant. And you wonder how this happened. The day before, all these buildings were compliant. The day after, these buildings are not compliant. And you wonder how this happened. In a similar manner, we went into panic, and we started evacuating buildings left and right. Now these buildings are unsafe. They're high-risk buildings that cannot be occupied by people. Well, the week before, we were building them and approving them. Anybody that would have come and started saying that these buildings were a high-risk occupancy would have been called a scaremonger. They would have been yelled at saying, oh, you're always trying to tell us that everything is going to burn down. But the day after, we're evacuating them. And it was not only a British phenomenon, the Germans followed, and it kept going. I mean, this has been like a rolling thing. And I can keep going. Some buildings were investigated in the US, mostly hotels. Organizations like Marriott or Hilton, they have a reputational problem. So they went proactively at looking into which buildings had these particular problems, and they started investigating them. The rest of America said, this will never happen in America. Okay? There was an article in the New York Times, headline, never in America. Okay? Now, we'll discuss that, okay? But that's the perception. Okay? We're still confident that the system here works. While in Britain, in Germany, in Australia, we're not confident at all. Okay? To the point that we're not only evacuating buildings, investigating buildings, you know, closing hospitals, okay? And it's only the beginning, because we have an entire typology of buildings that has been built in the last 20 years, which effectively in one way or another fits the same mold as Grenfell, okay? And the more we dig, the more we're gonna find, and the more we're gonna struggle to try to repair this, okay? So, but this is not news, okay? This problem actually existed before. So this is a building in Sao Paulo in Brazil, and it was the motivation for a film that probably predates all of you, which is called Towering Inferno. If you ever have a chance of watching that film, it is actually quite fascinating. You know, it replicates a lot of the things that we see today. So here is a building, high-rise building. This was a period where, in the 1960s, where plastics were beginning to be introduced into construction, and we had no sense of what were the consequences of putting plastics in construction. Okay? We didn't have the provisions, and the result was the external part. So it was a fire that started in a store, in a department store, and it propagated upwards extremely rapidly. Okay, there were many deaths in this building, in as much as there were many deaths in several other buildings that burned in a very similar way in the same period. So what was the response? So the United States had an act of Congress called America Burning. Okay, all of a sudden millions were poured into research to try to develop solutions for this type of problems. Okay? The United Kingdom had the UK Fire Act. They did exactly the same thing. The Japanese did the same thing. And it was a glory period of fire research. You have people like Irving Glassman here at Princeton, Foreman Williams. Everybody and their grandmothers was doing fire research, and money was pouring from every possible vault of government. Okay? And it was this. You know, all of a sudden, everybody was doing fire research, and it was something that was deemed to be incredibly important. Okay? And we solved the problem. So if you look at this, this is World Trade Center 7. Okay? So World Trade Center 7 had several fires started after World Trade Center 1 and 2 collapsed. Debris from the Twin Towers landed on World Trade Center 7 and ignited fires in multiple floors. These were all open floor offices. So the fires actually traveled all along the building from one end to another one, some of them clockwise, some of them anti-clockwise. They were burning at different levels. Not one of them went up and down. Okay? Effectively, the building worked. We had actually fixed the problem. We eliminated vertical flame spread. Okay? We did all the research that was necessary to try to come up with the knowledge that created a very simple solution that then we applied to try to solve the problem. Okay? The solution was straightforward. Okay? Effectively, what we did is we took a fire, and people did a lot of tests, and on the basis of the size of the window, you could actually establish what is going to be the flame projection. So you can calculate how high the flame is going to be and what is going to be the heat flux distribution of that flame. Then you went and did a lot of testing on glazing and showed what were the heat fluxes that glazing can tolerate. You put a safety factor, and you basically said, this is what is going to break glazing. So the glazing cannot start until the heat flux from the flame has decayed sufficiently that is below the breaking heat flux of the glazing. Very straightforward. So literally all we did was we said, okay, fair enough. This is a fire. Here is the window. A fire is going to project itself out of the window. Okay? You are going to get, if you go from here to here, there is going to be, this is a heat flux, this is X, and you're going to get a distribution that looks like this. Okay? Glazing is going to break at this critical heat flux. Okay? So up to this point, there shall be no glazing. Okay? So draw a line. This cannot be glazing. All this cannot be glazing. And I put a criteria of non-combustible. Is that okay? Minimum spandrel, that's what we call it. This was obtained through experiments. Ooh. Okay. So, huh? Oh, yeah, yeah. I'm turning around. So, basically, this was obtained through experiments. So, these were mostly done in Germany and the United Kingdom. Margaret Law, very famous fire engineer, compiled them and effectively wrote an analysis that basically predicted the evolution of the heat flux. Okay? And as a function of that, you got a critical height that was the minimum spandrel requirement. And then you guaranteed that every material that was going to be in place in here had to be non-combustible. Okay? So there you are. Here's your system. Here's the flame, the projection. This height here, from this point to this point, is the spandrel. And effectively, the glass above the fire will never break. In other words, you cannot penetrate the fire into the upper floor, and therefore it will never spread upwards. Problem solved. Okay? So from the 1980s to the 2005 or so, we had no multiple floor fires anywhere in the world. Okay? The deaths in tall buildings plummeted to almost zero, and all of a sudden we were safe. Okay? Then all of a sudden something happened. Okay? And that is just simply a selection. Okay? Something happened and you have buildings of all natures. Refurbished buildings, like an old place. Refurbishing buildings, the Windsor Tower in Madrid. New buildings, you know, in Dubai, in Shanghai, you name it. They're burning everywhere around the world. Until eventually, Grenfell. Okay? So first of all, we cannot claim that we didn't know this was happening. We have plenty of evidence that this was happening. So why do you think nobody did anything?
Because the deaths had plummeted.
Sorry?
Because of you just mentioned that the deaths in tall building fires was
First of all, nobody, well, that's, yeah, but once it started, people start dying. I mean, a lot of people died in Shanghai. So people were already dying. Yeah.
Well, since did you say New York Times wrote it on the front of their newspaper they were in America, I guess it's the same for the UK and the rest of the Western world, saying it's never going to happen here because...
Yeah, but I mean, this happened in the UK, this happened in Madrid.
Okay.
Yeah. They were happening even, I mean, there were a lot of them in Germany. There was a huge one in France.
And people died in those fires?
Oh, yeah. I mean, not in large numbers, but they did. So what do you think we did nothing? Well, money is always an issue, okay? But before you make the decision, I'm not going to do something because it's too expensive, you have to first quantify how expensive it is, no? Did we ever even take that step? Not really. Why do you think we did nothing?
I based on this, and it's not going to happen.
Yep. So we had still a lot of confidence in our building regulations, no? You know, in most cases, we tend to claim that this was happening because people were messing up, so they were actually not doing things right. Okay? We had excuses. Okay? But effectively, we still had a lot of confidence on our building regulations, so the process still, we believed it was okay.
I was more like not enough people died for the society to react.
That's when you lose confidence, no? When you get a big event, that's when you lose confidence. Okay? Now, the truth is that this happened, and then this is after Grenfell. And this is only, again, a very small selection. This keeps happening every other month. Okay? So 13 people died in this building. It's only a 6-story building. Okay? This one was in Hawaii. And people will claim it's not the same problem, but it's still the same problem because it was vertical propagation that eventually ended up killing a few people. This one is a very interesting one because this one started almost an urban conflagration. There was so much debris, burning debris, falling out of that building that it ignited the adjacent buildings. So you had cars burning in the street, other buildings burning. This one here is infamous for being the only building that I know at least that burned exactly the same way twice. It got fixed and it burnt again. And then they fix it again. So I'm sure there's going to be a third time. And there was this one in Sydney. Sorry, what's the one in Sydney? There was one in Sydney that was very interesting because they recognized that this facade system was a problem. So it was a law firm, and they decided to take it out. And as they were taking it out, they were using welding equipment. They ignited the facade and they burned down the building. Now, but what does that tell you? At the core, you know, what is really at the core of this problem?
Regulations are failing.
Yes, and why are we not doing anything about it?
Don't understand the complexity.
Yeah, we don't understand the problem. Nobody has a clue what to do. Yeah.
Might not even be a case of regulations failing. It might be that we create something that is not similar to the kind of regulations that we have already because it's not comparable. It's a different problem.
Yes. So effectively, the building that is classified in a certain way is actually should not be classified that way. Yeah, we'll get there. That's at the core of it. Yeah.
No, I have a question actually.
Yeah.
So here you talked about how that the safety distance had to be there before the heat
Yeah.
fell down and the flame couldn't propagate vertically. So for these cases, was this followed or no?
Technically speaking, yes. So in principle, all the materials used in all these buildings, technically speaking, are non-combustible. Technically speaking.
So there was that distance
And the distance is there, the spandrels are there, everything is there.
so basically it was some other mechanism through which
Yes. Yes. Yeah.
Kind of following on from the regulations failing, it's also the regulations have failed to keep up with the change, like the innovation in materials and systems. So we don't actually understand what they
Exactly.
So we can't answer it.
That's the problem. So the problem is that we're landing in a space where the system is now moving in a way that we just simply do not understand. So we cannot even understand how to transform our building regulations to make it work. And this is what brings us back to why do we need to understand these things? Because otherwise we still believe that our codes are making us safe without recognizing that they're only making us legal.
Is the other problem perhaps that, like, for example, the increased depth was based on empirical data? It wasn't actually from a fundamental understanding of physics.
Potentially. Yeah, so potentially that even then, we had a very simplistic solution that was based on empirical data, okay, that effectively might not be applicable anymore for the kinds of systems that we're operating. So all these are the questions. These are the real questions we need to address, okay? And the truth is that we haven't even begun to address any of these questions, okay? And this is why we cannot respond. You know, we're sitting there waving our arms, without really knowing exactly what needs to be done. Now, what is really a challenge, and what industry is very uncomfortable doing, is thinking or accepting their ignorance. Because if you really accept that you do not know how to address this problem, that basically means that you need to take a step back and create a system that is simpler, that we actually do understand. That implies relinquishing a lot of the gains, okay? Because as you see, these are very multifunctional systems. So I'm gaining at many levels, and taking a step back means relinquishing those gains. So it's very problematic, and we are in a conundrum where we have a system that we don't understand. We are paralyzed because we cannot fix it, and at the same time, we're unwilling to take a step back and deal with a simpler system. Because what many people will claim, okay, is why don't we go back to square one? We had fixed the problem. We know how to design this building safely. Is that okay? But we are not doing it because that will mean going back to bricks, which requires a complete relinquishment of many of the properties that new buildings have. So this is the last one. So this is a NEO building in Melbourne, in Australia. And this is a very interesting one because this was a building that was inspected after Grenfell, through a policy that the Australian government had of doing inspection of all these high-risk buildings. And it was deemed as a low-risk building. A few months later, it burned down. Okay? Which basically shows you how little we understand of what's going on. So, in this case, a cigarette was blamed for the fire, going back to probability of 1. There was a prior fire also in Melbourne. They called it Docklands fire or the La Crosse fire, and it was the same thing. It was an Airbnb. So basically, these people were renting their apartment as an Airbnb, and they had the misfortune of renting it to a smoking Frenchman, okay, who was smoking in the balcony, ignited a fire, and set the building on fire and destroyed the whole building. Almost $100 million in losses. So, does having a cigarette is an unforeseeable event in a tall building? Obviously not. Okay? Now, if that, so basically, the task force had actually called it moderate fire risk. Okay? Nevertheless, this is what they say. While most buildings, most of the building is not cladded at all, where there's any cladding that is used is compliant with the building authority standards, and this was tweeted, by the managers of the building. So there's all the words, the buzzwords. No, it's compliant, it's safe. Most of the building is not cladded, except for a part that is cladded and burned the whole building down, and all this, everything in there, and you can keep going with all these things. This building is extremely safe. It's around 90% made out of concrete panel construction, but the other 10% burns like crazy.
So what's this cladding again?
We'll get there. Okay, I'll touch on the cladding because this is what's coming left everywhere, no? What is this cladding that everybody's talking about? This is really interesting. The people said that they didn't hear the alarm until about 15 minutes after the whole building had to be evacuated. So people were sitting in there and they couldn't hear the alarm. Now, that was because of the way the alarm was set up. They were not supposed to hear it because it was a stay-put strategy. So only the people in the apartments that were on fire were required to listen to the alarm because those are the ones evacuating. Okay? The rest were not supposed to hear it. That's why they never heard it. So the alarm was working correctly. It's just that they were not supposed to get out. So it was smoky through the stairwell. And I'll talk about that a little bit because that's a very serious problem because it's your means of egress. Okay? And that's the backbone of your fire safety strategy. And it was full of smoke. The fire occurred, the sprinklers came on and assisted it's a Melbourne Fire Brigade, until the fire was dosed. There's a big question there, which is the other problem. We tend to over-trivialize solutions. Extinction is a very complicated problem, and we tend to believe that if we throw water, we fix the problem. So the fact that the sprinklers open doesn't necessarily mean that you actually control the fire. Nevertheless, people interpreted the fact that the sprinklers came on as the fact that so there's a confusion of performance. And the general manager, said that the building fire plan had worked perfectly. What is the basis of that? Nobody died. Okay? Was that appropriate? Was the building designed to perform this way? The building was designed to not have smoke in the stairs. The building was designed to give appropriate alarm to people. The building was designed to contain the fire in one floor. All these things were part of the design, and the building failed on every single one of them. So the building didn't perform appropriately. They were just very lucky that nobody died. Fundamentally, the buildings have massive safety factors, the robustness factor, and that's why they actually remain in place. And effectively, nobody died because this building had fat everywhere. Okay? So at the end, despite the fact that everything worked inappropriately, people still managed to get out sort of safely. Knee-jerk reaction. Without understanding the problem, then here we come. I'll be pushing for a nationwide ban on combustible cladding, really to further protect Victorians from being exposed to an acceptable fire risk. Okay? In other words, go back to square one. Nobody will take that, because that basically means relinquishing all the other gains that we have. So, this is a real question that we need to ask. So this is a Burj Khalifa. So this was New Year's Eve, 2 years ago. A small fire starts in the second tallest building in Dubai, 87-story address building. The whole building burns down under the watch of thousands of people. Okay? So, shall we accept this? Okay? So, what changed? Going back to the question of what is this cladding? Okay? What did change? So, what changed was the building envelope, and it was a massive technological leap. Okay? Comparable to the introduction of steel in construction. Now, the photograph in the back is not fortuitous. It's there for a reason. This is a timber beam, and these are steel beams. So this is a fire in a factory here in the United States, happened in the 1870s, and it was the beginning of the introduction of steel in construction. Steel exposed to heat effectively changes its mechanical properties, loses its mechanical integrity, and it completely falls down. Okay? Timber, in contrast, chars. As pyrolysis occurs, effectively you produce a char. The char protects the timber, and it slows down its degradation, and therefore the timber can last for a very long period of time. Furthermore, as the steel falls down, the ceiling collapses, or the roof collapses, which ventilates the fire, which lowers the temperatures, and the timber tends to self-extinguish. Okay? So, the perception...
Can you repeat the bit about the collapse that
Yeah, so effectively when the steel fails, the roof collapses. Okay, and the moment the roof collapses, it basically breaks. The heat and the smoke can go out, which lowers the temperature in the interior and results in the self-extinction of the timber. The timber doesn't continue to burn on its own. It loses too much heat and it cannot continue to burn. Okay? So basically the timber stops burning while it still maintains its structural integrity, while the steel has already failed very early on. So at the turn of the century, of the 19th century, people recognized that steel performed very poorly compared to timber. And they created a whole set of theory to try to establish a mechanism by which they could protect steel in such a manner that it behaved like timber. Okay, that was the objective. The original objective of trying to protect steel. We succeeded and came up with mechanisms of protection of steel. Now, the same thing happened with this concept of the building envelope. We changed the way in which we design buildings. Okay? And we created a building envelope. In the past, what we had was effectively, this is my concrete slab, I would put something on top, I would put something in the bottom. And the concrete slab protected me. What I did was, this was very inefficient. It created a fin through which you lose heat, so it was very difficult to manage energy in the building. So what we did was, here is my concrete slab. Now I'm going to create some sort of insulation in here, and what I'm going to do is a continuous building envelope. Okay? That way I prevent the heat from going out, okay? Because I'm insulating the tip of the concrete, okay? And I can manage acoustics, thermal, everything completely from the outside with a building envelope, something that completely circumvents the entire building. Sorry, encircles the entire building. Is that okay? So that was a change. So we did that in the late 1990s, and we changed the system from something very inefficient like this into something highly efficient like this.
So this inefficiency to efficiency is in the HVAC system?
Everything. So basically, very fast constructability. So you can construct this very easily. Now you hang the envelope from the concrete. So you can, I don't know if you've seen modern buildings, that they still haven't finished building the building, and they're already putting the envelope. So the methods of construction became infinitely more efficient because you could stack these things very rapidly. Okay? You didn't have to wait to finish the building to start building the envelope. Thermally, it was a mechanism to control heat transfer in a very effective way. So from a heat ventilation and air conditioning systems, you had a very efficient solution to the problem. Acoustically the same, because you have a continuous system with no acoustic bridges. So you could control the acoustics very efficiently. You name it. You have multiple advantages at every possible angle. So these particular systems are highly, highly efficient when it comes to everything but fire. Okay? So all these drivers were pushing very strongly at the time. So we developed all these construction methodologies. I had a meeting at the National Science Foundation here in the US a couple years ago. And it was quite interesting, no? Because if you go to the website of the National Science Foundation in the US, it says NSF does not fund fire research. It says it explicitly. They do not fund fire research. Okay, so they invited me to give a talk because Grenfell had just happened. So I came in there and I had looked at the statistics. Okay, so I looked at all the awards that they had made in the last 10 years. What were the awards? Building insulation systems, new facade systems, timber buildings, you name it, composites in buildings. So I put all this, and there was approximately $100 million that had been given in the last 10 years to fire. Not to fire research, but to create fires. So basically government incentives drove this because at the end, the bottom line is huge. Can you imagine reducing the energy consumption? To what extent you can reduce energy consumption by doing this? Enormously. Buildings are the biggest energy consumers in the world. So if you can cut energy consumption by 20%, you're saving yourself an enormous amount in energy bills. So the drivers were incredibly powerful. Okay? So everybody was pushing for new construction methodologies, and nobody was putting a penny in trying to understand what the consequences of that was. Okay? So one of the real innovation, going back to the question of the cladding, was the flammable insulation materials and the concept of encapsulation. Our building regulations still required that all materials used in facades had to be non-combustible. How do you circumvent that? You put all your insulation, okay? This is all combustible. Okay? And what do you do around it? You put a non-combustible encapsulation. Okay? So this is non. That's how you get around it. Okay? So you have aluminum composite panels, the cladding, which is aluminum, polyethylene, aluminum. You have rendered insulation. It could be expanded polystyrene, polyurethane, polyisocyanurate with a ceramic rendering. Okay? You name it. You have many, 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 many variants of encapsulation. The material facing the outside is still not combustible. But inside, somebody described it as petrol. And I was listening to one of the talks earlier, and Henry Curran was talking about the heat of combustion. Of course, I mean, polyurethane or polyethylene have the same heat of combustion as gasoline. Okay, that doesn't mean they're the same, but they have the same heat of combustion. So effectively, you created this concept of encapsulation. Now think, by creating encapsulation, how did we change the problem?
We found a way of passing the test without actually...
What test?
Standard testing. So like
But what test? What were we testing for? Combustibility, no? So before we had a test that determined if a material was combustible. How do you determine if a material is combustible? What is the property of a combustible material?
When you remove the fire that starts it, it continues to burn.
Yeah, so basically you produce energy in sufficient quantities that the reaction is self-sustained, no?
Right.
Okay? So that's the definition of combustible material in one way or another. In other words, you have a material that burns. Okay? Do we agree? So if I cover it with steel, then it's not combustible. No? But how have I changed fundamentally the problem?
It's combustible inside, so if we keep heating up the
Fire inside
panel,
should
it's
be.
gonna suffer inside.
Well, yeah, but what does that mean? So the fact that if you keep heating the panel, eventually something is going to happen. But what is going to happen? Yeah.
If the speed of the encapsulation gets compromised, then it's exposed to air and it's also exposed to a very hot surface, which can probably cause.
Yeah, but how have we changed the problem? I agree that that's what we're doing. So you're basically getting this thing to fail, okay? And therefore it's breaching, and it's igniting the combustible material. So how have we changed the problem? Before we had a test that just evaluated if you had a heat of combustion that could actually sustain burning, no? Easy. We've known this since Lewis and von Elb. Yeah.
Time dependent now?
Well, it adds a big variable, no? Because before it was not time dependent. All what I was doing was effectively addressing if I had enough heat of combustion, no? Very simple test. It doesn't have to be time dependent. All I need to know is that it has enough heat of combustion.
So
Now I have a time dependent problem, but what is really the problem that I have now?
the test might be a problem itself.
Well, that's a result of it. But what is the problem that I have now?
Change the heat transfer.
I'm definitely changing the heat transfer, which complicates the problem. But what is my problem?
You're not testing material.
What am I testing?
System.
Well, the product is the result. So effectively, we're talking about the failure mode is that you breach. Okay? So what is the problem that you're addressing? Are you addressing a combustibility problem? A mechanical problem? So all of a sudden, we were dealing, all our tests, our entire system is operating on the basis of establishing combustibility. If inside that box there's polyethylene, I have no question about it that it burns. It is combustible. Any of my simplistic tests can tell me it's combustible. I have no problem establishing that. If what's inside there is concrete, it's unequivocal, no? I'll put it in any furnace that you want and concrete will not burn. Do we agree? Simple. Now tell me, how are you going to test if this system doesn't fail mechanically? It's a heat transfer problem. It's a time dependent. Okay? It's a system problem. It's everything.
I think we don't have those tests.
We don't have anything. So we shifted the problem completely, and we didn't recognize that we were left with nothing. Okay? That's the problem. Okay? So all of a sudden, encapsulation created that big, etc., everything. Hell broke loose, and all of a sudden, I cannot address the problem. Okay? So it is not one problem, it's many problems. Okay? So this is what happens. So this is the Aqua building in Chicago, and this building was designed on classical terms. So if you look at it, here you get the concrete slab protruding, just like I did here. So it protrudes, and in some areas where it doesn't, so I don't get the spandrel, you can see the cuts is because they actually have a balcony. So inside there's a spandrel. So they actually did it correctly. So it's the old-fashioned way. Okay? So effectively, this length gives me that spandrel that will deflect the flame away from the window. And wherever I don't have enough, then what I do is I put a balcony that is made of non-combustible materials. Okay? So it's basically the conventional way. This is one of the most criticized buildings ever. Why? Because it has high conductivity thermal concrete slabs emerging out in Chicago. So every winter in Chicago, the people in the Aqua building are freezing. Okay? And every summer in Chicago, the people in the Aqua building are boiling. Okay? So we do have a problem with the Aqua building. It either boils or freezes. Okay? And it's an enormous, everybody criticizes this building. Everybody hates this building. It's beautiful, but everybody hates it. Okay? Because effectively, has fins emerging from the building. So it's very problematic. Okay? So this is a conventional case, and basically this would have looked like this. So you have a concrete slab that protects you. You have non-combustible elements above and below that create the spandrel, so the flame can never break the window above. Okay? So we test this for non-combustibility, we test this for non-combustibility, and this barrier, we tested for what we call fire resistance. In other words, this barrier will not be breached for as long as it takes to burn all the fuel down. Okay? Burnout. Nothing moves. Okay? So this is sitting on top of this, so it doesn't move. This is a fixed concrete element, it doesn't move. And this is hanging from the top. Very simple solution, one single set of testing criteria, combustibility. Okay? Is that okay? So then all of a sudden, Lord Foster designed this building, which was an absolute landmark in the 1990s, the first true building envelope. It's called the Gherkin, originally called Suisse-Arrêt, and effectively this beautiful continuous system that envelopes the entire building. Now what you get is a lightweight structure on top, a heavyweight structural component in the bottom, on the side, and a connecting point. Okay? This connecting point becomes the weakest link because it links a very lightweight structure that will heat up very rapidly to a very heavy concrete slab that will heat up very slowly, so there will be relative motion between them. What is the outcome of the relative motion? Mechanically uncertain. Okay? We didn't pay much attention, and all of a sudden we went from this to this. Okay? That's what happened. And now we're having 1 million of this, and we don't know what to do with them. So we have two forms of strategy. One is a prescriptive design, and the other one is a performance-based design. Most of these buildings were done according to code. Okay? So people trusted the code and worked with the code. So effectively, they implemented a strategy. Okay? And the strategy is pretty straightforward. Here's your building. Building has means of egress. And what I'm going to do is put, for life safety, a smoke detector. Okay? I tell people there is a fire. Fire is there. Then I'm going to guide them to the outside. In most countries in the world, you will have a very relaxed man, and the signs will be in green. In this particular country, the sign is in red, and as you can tell, the person is truly in panic. Okay? But anyway, that's not necessarily reality. But so then, once you get people moving, then you protect you design your means of egress in such a way that you allow everybody that you let in to go out. Okay? Obviously, there's issues with people with disabilities and so forth that you have to take into consideration because it is a real serious problem. To be able to address that and allow proper means of egress, you don't allow the smoke to get into your means of egress. So this kind of situation where the smoke migrates up through the shaft of the stair is unacceptable. Okay? So you will protect your stair by using the concept of compartmentalization or compartmentation. Okay? In other words, you create walls around the stair and you make sure that the stair doesn't fill up with smoke. Okay? So the walls are going to be designed very carefully so they're not breached by the fire. And the doors will be designed very carefully in such a way that they're not breached by the fire. And those designs even include, for example, the panic bars and so forth. Everything is designed very carefully so it's not breached by the fire. You have response. In other words, you can have sprinklers to control the fire. You can have the firefighters. You have to give them water provisions. And you have to give them means of access. Okay? So effectively, firefighters are there to take care of where it cannot be managed. Okay? Sprinklers are there to try to control the fire before the firefighters arrive. Smoke detectors are there to start the process of egress, and the rest is compartmentalization, so that the smoke doesn't get to the places where people are using to evacuate. On top of that, you have to guarantee that your structure remains stable. In other words, you protect your steel, for example, with thermal insulation so it doesn't heat up. So that's your context. This is what we implement in a building to make it work. Okay? So if we look at this, you know, most of these things are purely common sense. When it comes to code, I have rules. And the rules will say you have to have this many fire hydrants in a certain place. It says you have to give access to the fire truck so that they can approach the building. It says you have to put your signaling in a way such that is appropriate. There's no engineering involved in there. Nothing. Pretty straightforward. Okay? So all these things, none of them are engineered. Okay? In a similar manner, you create testing standards that allow you to establish if this designs of walls, designs of doors, designs of beams, concrete slabs meet the required criteria. So if you test them and they pass the test, then we're all fine. So there's no engineering. All the systems are qualified. You send them to US, you send them to anyone that can give you a CE brand in Europe, and effectively they're all qualified. So long I pick the right one, it's all pure common sense. No engineering involved in any of these things. Okay? Now, the same thing when it comes to everything else. So if you look at the compartmentalization, if I have put all the components right, then I don't need to do any engineering. It's all there, and it works. With detection systems and sprinkler systems, it's about the manufacturer. They will tell me where to put them, how many to put them, how to space them, so that they work appropriately, so it becomes all common sense. There's no engineering. Okay? And the same thing with the design of the means of egress. We have very simple rules that tell me how wide the stair has to be, how the steps have to be designed. Everything is all set up in the rules, gone. All common sense, no engineering. This is how unprepared we are. Because effectively we have a set of rules. Those rules are very detailed. They tell us exactly what to do. We don't need to have a brain. It's not required. Okay? All you need to be able to do is to read, so that you can check all the boxes. Okay? Now, what happens when somebody changes a rule?
Still have the same recipe, keep applying it until we failure.
Yeah, if we have no brain, we cannot respond. So this is what we did for 30 years. You know, we standardized the whole thing, and then all of a sudden somebody changed the rules. And then we're wondering, yeah, what can we do now? So effectively, then we land on this. This is how we innovate. What's the difference between that plane and any other plane?
Electricity instead of hydraulics.
And what else does it have?
A lithium power supply instead of a combustion APU.
And we've seen a lot of failures of that type, no? What about the fuselage of the plane? What is it made of?
Composite.
Oh, which is a plastic, no? Do you know how we test the fuselage of a plane? One of the most successful fire safety strategies is the crash landing of planes. We have the capacity to pretty much get, if people don't die in the crash, and there's a subsequent fire, which always happens, people can get out of the plane safely in about 1 minute. And the success rate is extremely high, because we have it worked to the second. Okay? Everything has been done in a way such that we have that period of time to get everybody out, and it actually works. Okay? Now, the way we test that that works is that there is a test that you put the fuselage structure, and you put a torch that hits it, and then you measure the time that it takes to breach the fuselage. We're still using the same test, but now with composites. And the question is, does it actually work? We have no sense. Okay? And I can go through every industry, and I can show you very similar examples. Petrochemical industry, I mean, we saw it with the platform Horizon, is gone beyond management. Okay? And we haven't changed a thing. Now, the petrochemical industry became so standardized that we truly have no brain. It's rules, 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 and all the people that actually designed those rules have retired. And nobody has a clue, we just keep doing it. And these oil platforms get bigger, you know, petrochemical plants get bigger. Mining, we're going back there, you know, to the old times of coal mining. The way in which we have extended mining operations is extraordinary, and we haven't changed the rules at all. Transport, you name it. I mean, trains, size of tunnels, plastics that we're putting in the trains, and we're using exactly the same rules. So let's break for another 10 minutes, and then we'll bring it to the end until 5:30, okay?